Hello friends, welcome to Academy's platform for class 11-12 physics. Today we will consider a MCQ type problem from electrostatics. See the statement of the problem. A tiny spherical oil drop carrying a net charge Q is balanced in steel air with a vertical uniform electric field of strength 81 pi to 10 to the power 5 divided by 7 volt per meter. When the field is switched off, the drop is observed to fall with terminal velocity 2 into 10 to the power minus 3 meter per second. Given G, the acceleration due to gravity, as 9.8 meter per second square, viscosity of the air 1.8 into 10 to the power minus 5 Newton second per meter square, and the density of oil 900 kg per meter cube. The magnitude of Q is, which one is correct out of these four options that we have to find out. Now, see the problem. A oil drop, say the radius of the oil drop VR for the time being, is balanced in steel air with a vertical uniform electric field of strength such and such. Electric field strength, you see, it is E. Consider E is equal to 81 pi into 10 to the power 5 volt divided by 7 volt per meter. Alright, now this oil drop is in air actually, is balanced in steel air. So what are this is the weight of the oil drop. It is kept in air actually, and this is the oil drop. So weight of the oil drop is 4/3 pi R cube d oil into G. And since the oil drop is in air, there is a and weight is actually acting in the downward direction. You know, it is gravitational attraction, and there is a buoyant force of air acting on the oil drop in the upward direction. It is weight of the displaced fluid. So weight of the displaced fluid is actually 4/3 pi R cube. That is the volume of the displaced air, and density of air, if I call it d oil is density of oil, which is given as 900 kg per meter cube, 900 kg per meter cube, and dAr is density of air. Alright, multiplied by G, that is the buoyant force. Now, buoyant force is acting on the oil drop in upward direction. Alright, so net weight of the oil drop, net weight of the oil drop is actually 4/3 pi R cube d oil minus d air into G. This is the net weight of the oil drop, which is in the downward direction. And this net weight, which is W minus B, it is acting in the downward direction. It is being balanced by an electric field, electrostatic field. So electrostatic field, electric field is in this direction. So electrostatic force, this is charge of the oil drop. So EQ, which is the upward electrostatic force, is equal to W minus B. So equal to, this is equal to 4/3 pi r cube d oil minus d air into G. So this is clear. Now, what happens when some spherical or some sphere falls in a viscous media? Oil is a viscous media. So what happens? Just let us recall. Had it fallen in the free space, the oil drop, then what happened now? Not free space, it is just consider that oil drop is falling, there is no electric field. There is no electric field, the oil drop is in the air and it is falling in the air. The net force acting on the oil drop is W and this is air. This is the buoyant force. So net downward force is W minus B, where we have already written the expression for W and B. W equal to 1/4 pi r cube d oil into G, and B is 4/3 pi r cube d air into G. Now, when the oil drop falls in the air, through the air actually, net force acting on the oil drop is W minus B, which is downward, and as a result, the velocity of the oil drop increases as it falls down. But since it is in a air media and air has a viscosity, so there will be a viscous force acting on the oil drop in the upward direction, and I call this viscous force as V. It is falling down and there is weight, there is buoyant force, and because of viscosity of air, there is a viscous force acting on the oil drop in the upward direction. So the net force is W minus B plus V. V is the viscous force on the oil drop offered by the air media. Now, viscous force increases with velocity of the oil drop. That you know. Oil drop's velocity is increasing because there is a net downward force W minus B. And as the velocity increases, the viscous force is increasing. And ultimately, when W becomes equal to B plus V, then the oil drop falls with terminal velocity. And the expression for terminal velocity, and if I say V is the terminal velocity, small v, then when the terminal velocity is achieved, definitely this value becomes 0. W minus B plus V is 0. That means the net force on the oil drop becomes 0 when the oil drop achieves the terminal velocity. So mechanism is, as the oil drop falls down the air media, its velocity is increasing, and as the velocity is increasing, the viscous force offered by air on the oil drop is also increasing. And ultimately, these two forces are not changing because these two are W and B. This is constant, this is also constant. So, as the viscous force is increasing, W minus B plus V is decreasing, and ultimately, when W becomes equal to B plus V, the ball sphere or spherical ball starts falling with a constant velocity, and that velocity is the terminal velocity. And if I call V as the terminal velocity, this is small v and this is capital V. This is the viscous force. This is viscous force. And when the terminal velocity is reached by Stokes' law, this is the statement of Stokes' law, the viscous force, which we call V, we can also call it A, is actually 6 pi A R B. 6 pi A eta B. Sorry, 6 pi R eta B. 6 pi R eta B. That means when the terminal velocity is V, it moves with constant velocity V, moves down the air medium with constant velocity V, and at that stage, the value of viscous force, which is acting in the upward direction, I call it V or capital F, whatever, is equal to 6 pi R eta V. 6 pi R is the radius of the sphere, spherical ball, eta is the coefficient of viscosity, and V is the terminal velocity. Okay, now at this stage, when the terminal velocity is reached, I can write this equation, W minus V plus V is equal to 0. Okay, so this is the net force W minus V downward, and this is actually W minus V is equal to V. Okay, so W equal to, from this actually I can write V plus V. So W minus V is equal to V. I call this V or F to avoid any confusion. Call this F. Is it clear? That means on the oil drop there is, I call this viscous force as F. So net upward force on the oil drop is V plus F, and downward force is the weight of the oil drop. So V plus F is equal to W. So F is W minus V. So F is W minus V. So this equation we'll use to solve this problem. So what is F 6 pi R eta V is equal to 4/3 pi R cube W minus V, rho d oil, density of oil, minus d air into G. Alright, so if I just write down the equation, what happens? Let us see. This equation, if I just write down, what happens? So 6 pi R eta V is equal to 4/3 pi R cube d oil minus d air into G. So V equal to eta V is equal to 2 2 by 9 R square d oil minus d air into G. So R square becomes 9 eta V by d oil minus d air into G. Or you can write R equal to 9 eta V by, and there is a 2 over here, 2 d oil minus d air into G. Okay. Whole to the power, this is whole to the power half. Alright. Now, with this background, let us try to solve the problem. So, once again, what we derived in the last expression, that means 6 pi. Let me write once again the expression. Six pi r eta v is equal to 4/3 pi r cube d oil minus d air into G, and therefore R equal to what we have found, 9 eta V by 2 d oil minus d air into G whole to the power half. Now the timing, so this expression we have found. How V is the terminal velocity, V is the terminal velocity V. And this is the expression. Eta is the viscosity. This is eta. Okay. And terminal velocity is V. This is the terminal velocity. Now, the spherical oil drop, when the field is switched off, then the question of terminal velocity comes. But normally, the tiny spherical oil drop carrying a charge Q is balanced in steel air with a vertical uniform electric field. Therefore, we have already seen QE. This is the oil drop. QE is the net upward force, and net downward force is W minus P. It is at rest. Oil drop is at rest. So there is the viscosity because it is not in motion. So the spherical oil drop carrying a net charge Q is balanced in steel air with a vertical uniform electric field of strength such and such. So there is no viscous force in steel air, and therefore it is balanced with QE and W minus B. So QE equal to W minus B. So 4/3 pi R cube d oil minus d air into G. Okay. So Q is how much? Q is equal to 4/3 4 by 3e pi R cube is this much. This multiplied by 3 by 2. So here one d oil minus d air into G is there. and then 9 eta v whole to the power 3 by 2 by 2 into root 2 into B oil minus D air into G whole to the power 3 by 2. So what happens? Q becomes 4 pi divided by 3. Electric field is given as how much? 81 pi. So it is, let me write down this expression, how much it is? 4 pi into 3 into 81 pi into 10 to the power 5 into 7. So 4 pi by 3e is 4 pi by 3 into 81 pi 10 to the power 5 by 7. This 7 goes up, and then 9 eta v whole to the power 3 by 2, then 2 root 2, and this I get root over d oil minus d air into G. Okay, so it is this pi, we cancel each other. So what happens? I get 28 you can write, it is 28 by 243 into 10 to the power 5. Here what happens? D oil, there is expression for V, this is 9 eta V whole to the power 3 by 2. So it is 27, 28 into 27 eta into V whole to the power 3 by 2. Okay, and in the denominator, what we get? 2 root 2. And if we take d oil common, then 1 minus root over d oil into G, and then 1 minus dr by d oil whole to the power half. So since dr, density of air, is much less than density of oil, so I can neglect this term. So ultimately I get this expression, 28 into 27 into eta v whole to the power 3 by 2 by 243 to 10 to the power 5, 2 root 2 square root of G into d oil. And if you find out this expression, because all data are given, eta is given, v is given, d oil is given, G is given. If you substitute all these values, you get 8 into 10 to the power minus 19 coulomb. So this is the expression for Q. Okay. So this is the technique how you can solve the problem. So answer is 8 into 10 to the power minus 19 coulomb. This is the correct answer. Answer is D. So I hope you have understood how to solve the problem. Once again I repeat, when the electric field is not there, the oil drop is falling in air through a terminal velocity v. That means when the oil drop is moving with terminal velocity small v, you say, then the net viscous force acting on the oil drop in the upward direction is actually 6 pi r eta v, and the weight of the oil drop is actually 4/3 pi r cube rho oil into g, and there is buoyant force acting on the oil drop in the upward direction, which is also equal to 4/3 pi r cube, which is the volume of the displaced air, then rho air into g. Remember, this force is a viscous force acting in the upward direction. This is weight of the oil drop acting in the downward direction, and buoyant force is acting in the downward direction. So when the body is moving with constant terminal velocity, that means at that stage there is no net force on the body. So F plus V must be equal to W. So 6 pi r eta V is equal to 4/3 pi d oil minus d air into g into r cube. Now itself you can take 4/3 pi, take d oil 1 minus d air by d oil into g into r cube. This quantity I am neglecting because d air is much less than d oil. So I am left with 4/3 pi d oil g r cube. Alright. So from this expression, what you can do? So 6 pi r eta v equal to 4/3 pi d oil r cube into g. So from which we can write r square equal to 9 eta v by 2 d oil into g. So from which we can find out the expression for r, which is nothing but square root of this. So this is the expression for r. Now what happens when, if you consider the first part of the problem, a tiny spherical oil drop carrying a net charge is balanced in steel air with a vertical uniform electric field strength, which is given as 81 pi × 10⁵/7 volt per meter. That means it is balanced, means it is at rest. Electric field is in this direction. So force due to electric field on the oil drop is E into Q, which is equal to net weight of the body, which is W minus B. So EQ equal to W minus B. This gives what? If I just remove this part now. So EQ equal to 4/3 pi R cube d oil minus d air into G. So again, neglecting dr compared to d oil, I can write it is 4/3 pi RQ DON into G. So Q becomes 4 by 3 E pi DON into G, and RQ R we have found, so it becomes 9 beta V by 2 DON into G whole to the power 3 by. So from this expression, if you substitute all the values, E is given, DON is given, G is given, eta is given, V is given, terminal velocity, then we get Q value of Q as 8 into 10 to the power minus 19 coulomb. So I hope you have understood how to solve this problem. This is a very simple problem. Only two parts. There are two parts of the problem, and this is the connecting equation between two parts, and you can finally find out the value of Q. Okay. So hope it is clear. If you have any doubt, you can revert back to us. So this is the solution. Thank you for your listening. Thank you very much.